SQNR, so that's a 16 plus 1.76. So this just recap what I already told you. So it is a theoretical limit of ambient ADC. This is really the best SNR you can possibly get. Okay. In real life, there's gonna be circuit noise, there's gonna be mismatch, there's gonna be a lot of non-linearity. There's no way you can go beyond this SQNR. There's another good reason why you need to know this number. Sometimes, when I review people's papers, they say, oh, I designed for 10-bit AC, I get 80 dB SNR. Then you say, okay, try harder next time. Okay, so you just reject the paper right away, right? So be careful, right? So sometimes people forget about this, right? So sometimes they report the SNR number is even better than SQNR, right? So that's always fishy, right? So that's allow people to reject your paper right away, or your product right away. All right, so this SQNR is from the sine wave input. For real input, as I just said, you actually need to run through the examples, right, to know what's the actual SQNR that you are expecting. All right, so this is the table just to show you the conversion. Right, 4-bit is about 25 dB, 8-bit about 50 dB, 12-bit 74. If you want to have some 3-digit SQNR, you need a 16-bit. 16 bits, you get close to 100 dB. So that's what people are talking about. If you want to have above 100 dB, you are really looking at 16-bit and above. Okay. People do build the ADC above 16-bit, just so you know, especially for audio, right? So 20-ish bits, 24 bits. Is 146 dB. Remember I talked about the human ear is very sensitive. Yeah, so actually indeed people build the 20-ish bits. When you get to that level, the SNR is so tough. Remember in 536A, we're gonna go through all this noise analysis. That's no joke. Absolutely no joke. At that level, any tiny, teeny noise, flicker noise, shot noise, all the noise, it will come into play, right? So if you, in the future, you are designing these high SNR systems, you're gonna find out your noise analysis will become so good. If you go back and take that midterm exam, you're gonna nail it right away. You're gonna nail the entire midterm and final exam. Anything related to the noise analysis. Okay. So that's SQNR. So in real life, how do we analyze, right? So let's say you design your wonderful ADC, and then say, oh yeah, I really need to see. Actually, no, right now, sorry, we are not even designing ADC. You just design the model. Okay. So remember I talked about this staircase, right? So in one of homework, you're gonna build. Okay, yeah, this is staircase that I'm gonna have. So how do I test the SQNR? Okay, how do I test SQNR? So it turns out this is not so different from what you did in 536A. Right, in 536A, you look at, you design amplifier, right? You inject a sine wave, right? You look at the output spectrum, I suppose, right? You look at spectrum. And then you look at the spectrum and you try to find out the SNR. So here you do exactly the same thing. Okay, so what you're gonna do is that, you inject a sine wave. So let's say if F in is in this particular example, right? So I do this in my lab. So I have a 127 Hertz sine wave input. I assume my sample rate is 1 kilohertz, so 1024 Hertz. Okay, I assume that's a 10-bit ADC. So what I did is I just created that 1024 steps. That's all I did. I inject this. I observe for 1 second. So I'm gonna collect samples, right? Actually, how many samples do I collect? In this MATLAB, how many samples do I collect? Input 127 Hertz, sample rate 1024 Hertz, 10-bit ADC, I capture exactly 1 second. I try to mimic this ADC as if in real life is 1 second. Yeah, I don't mean that my MATLAB simulation time is 1 second. That's not what I meant. I created MATLAB to mimic as if I run this ADC for 1 second. How many samples do I collect? ADC is taking the sample, right? Taking a sample. Remember that delta function? One delta function is one sample. Two delta function is two samples. Delta to delta, the sampling frequency is 1024 hertz. I collect for 1 second. How many samples do I have? 1024 sample, right? Does everybody agree? I know it's afternoon and it's Friday, right? Today's Friday. Yeah, I know it's not the best time. Okay, 1024 sample. Okay. So guess how I plot this spectrum? How do I plot this spectrum? In MATLAB, I take 1024 samples. How do I look at the spectrum? I do FFT, right? Or DFT, yeah. So that's exactly what I did. I take this 1024 samples, I do FFT. Remember, we look at the 0 to fs over 2, do you remember? In the signal processing, because everything is repeating by itself. So when you do MATLAB, usually they just plot just up to half. So basically Nyquist frequency. Okay, so they will plot to half. So 1024, half of that is 512 hertz. Okay, so this is mapped to 512 hertz. Okay, so 1024 samples. I do FFT, so I get how many bits do I have? How many samples when I do FFT? 1024. Okay, 1024 samples. Okay. All right. So I see a tone right there. Do you guys see a tone right there? What is this? What obviously this white high tone. What is that? Input signal. Very good. This has to be my input, right? So this is my input signal. And by the way, you should do the same thing. Okay, in your homework, you're gonna create your own model, right? And inject a sine wave. That's the first thing that you need to check. Do you see the input? You do see input, and what's my frequency? 127 hertz. Yeah, it's just right here. So it is 127 hertz. So that's the first sanity check. In the future, you should do the same thing. Not just this homework, coming homework, you do this, but also in the actual ADC schematic that you design, right? Or one day you buy your ADC from TI or whatever, right? You check this out, you do FFT, you should see your input. Okay, that's the first thing that you need to check. What are these? So I do see this guy, this is my input, which is sine wave. That's beautiful sine wave, that's no problem. What are these? Condensation noise, right? That be error that we just analyzed. Condensation noise. What kind of noise does this look like to you? White. What is a white noise? What's the definition of white noise?
Just flat over the spectrum.
Flat, and in time, is there correlation? From sample to sample, is there any correlation?
No.
No. So they are independent. Is it true? We talk about this B error. Do you believe from sample to sample the B error are dependent or uncorrelated?
Define from sample to sample.
Sample just like ADC, right? So you condense in time and condense in amplitude, right? So the first sample, that's the first delta function that you multiply with, right? So you take first sample, second sample. Okay, so if you need to visualize, so if this is my input, ADC, first sample, second sample, third sample, fourth sample, yeah. are those V error associated to those samples are independent or they are dependent or they are correlated? Tricky, huh? Yeah, I know it's Friday afternoon and it's hard. Okay, so it really depends on the input waveform, right? So if the input coming like somewhat random, right? So it can be anything like with your Wi-Fi signal, right? Or something with your 5G, you know, your cell phone. Who knows what your friends are going to call you from or talk about, right? So all those are random. So yeah, so all these sample value are really random. It has actually no correlation, right? So they have no correlation to each other. So of course the V errors, of course they are uncorrelated, right? So that's why you see it's kind of almost like a white noise. Not much correlation. However, you know, in some cases, so I'll go back to my extreme case. If my input is a DC signal, go back to this. If now I change my test signal from 127 Hertz sine wave to a DC signal, what is my spectrum looks like?
Only at 0.
Only at DC, you have a tone. That's my signal
And
and your noise. That's exactly right. Very good. Your signal, your noise is all at DC. You no longer see this white noise, right? Okay, so yeah, so that's it's really signal dependent, and this kind of go back to what I said earlier. We need some pre-assumption. The pre-assumption here, typically when we analyze this ADC like sine wave, right? So you pretty much uniformly distribute those V errors, right? So that's why you get this more or less like white noise, right, from your V error, your condition errors. But just noting that, you know, it really depends on whether you run into some special case, your input is always around some small range, then your spectrum may look a little bit different. Yeah. But by and large, you know, if you exercise, you know, within this range, more or less uniformly, you are good. Okay. So this is pretty much the spectrum that you usually would expect to see. Okay, so I see all those tones right here, and you say that correctly. This is a condensation, right? If I sum up all these spikes power, so I do square sum, what do I get? If I sum up all the spikes, you see a lot of spikes, right? How many spikes? So in total it's 1024 spikes, and one is being the signal. So you have another 1023 spikes. Sometimes people call beats. Yeah, so you sum up all this power, what do I get?
One. The step size squared over 12.
What is that magic equation? I suggest you to remember. Of course, you have to look at the normalized delta, right? So you normalize that, you know, then you get this power. So that's exactly. Okay, so let's further look at this, how this quantity noise, why it's come up like just a bunch of spaghetti, you know, randomly distributed. Okay, so let's consider this case. Remember I said that ADC has two things. One is quantized in time, the other one is quantized in voltage or amplitude. What if I get rid of the quantized in time for now? I have an ADC, I quantize in amplitude. Does that work? I know so far I have been telling you that, oh, ADC, first you need the sampling circuits. So you take a sample like this, take a sample and then you quantize, right? What if I don't do that? I just quantize the amplitude. So this is what you're gonna see. This is your analog signals. If I just quantize the amplitude like this, is this ADC? So every time you cross the level, you're gonna create a sample. That's why you see a jump. You see this? Yeah. Is this a digital signal? Yes? No? It can be represented by the digital code, right? So that's why it's digital signal. What feels strange is that it comes at
Ununiform.
different time. Okay, so that's non-uniform. So far, and also throughout the semester, I will focus on the ADC where it will be like this. So you sample this at a fixed constant time. Okay, so that's what I'm gonna call that as a uniform sampling ADC. In the whole world, 99.9999% of ADC, they are uniform sampling. That's why people don't even bother to call that as a uniform sample ADC. Because this is a class, and I want to give you a comprehensive view. It is not the only ADC in the world that, you know, oh, you have to take at a constant time, then you do quantize. You can do the other way around. You quantize the amplitude, and you don't quantize the time. Okay, so it becomes a signal dependent samples. Okay. Yes.
No, but if you do this, then at the same time instant you have to resolve all your ADC bits, right? So you don't have the luxury of sampling the signal and keeping it.
No, so you don't have a sampling. Yeah, you don't have a sampling signal. You don't have a sample signal per se.
I mean, you don't have a signal, input signal level that you can resolve your bits one by one like a SAR ADC.
No. Yeah. So it's, yeah, forget about what kind of ADC, right? So we're not even there yet. So just imagine, you know, if I can have some circuits to compare, that you cross the level, and then say, oh, you cross this level, okay, so you're gonna get a 001 code right here. It's possible. It will be completely different ADC than what you probably have if you are lucky enough to learn some of ADC. It's completely different. Yes.
So, what do you mean? This input dependent. What is
Sample time.
dependent on
The
it?
sample time will be input dependent, right?
Oh, the
Just depends on
sample
when time. Yeah, the sample time will be input dependent. Depends on when you cross the level. Okay. All this ADC. So this is still ADC. Okay. By the way, it's still called as ADC. Okay, because you know you can represent in a discrete code. Okay, you still go to a digital world. It's just the time is kind of funny, right? This is what I'm gonna call that as a non-uniform sampling ADC. So this ADC, actually you'll be surprised. People actually have used this kind of non-uniform sampling ADC before. Okay, so just like what I told you, right? So whenever you cross the level, you change the code. Okay, so this sometimes people call that as a cross-level sampling or level crossing, you know, ADC. So if you search the literature, it exists. It exists. Okay, people do use that kind of ADC. You know, sometimes in the low power biomedical, you know, circuits, they do this. They don't. The beauty of this that you don't need a clock per se. This ADC you need a clock to sample this, right? Here you just let it run. Okay, you cross the level, whoop, you change the code and you do something. Okay, so that ADC itself is clockless. Sometimes they also call clockless ADC. Okay, so you do that, and then you have all this you know, range of, you know, different property, and then like I said, you know, the sampling time are signal dependent because really depends on when you actually cross a particular level. So this is almost like analog-ish. You see this? You see all these staircase, right? So you see the steps case are different width. It's almost like analog signal, right? Almost like analog signal. It's just that, you know, your Y or your amplitude is not precise. So it turns out that, you know, this kind of ADCs And by the way, I don't have time to go over all kind of non-uniform sampling ADC. So my research group, we have been working on non-uniform sampling ADC more than 10 years now. So we have done all kinds of non-uniform sampling ADC, and sometimes we found some very interesting properties. In fact, we even use this non-uniform sampling property to apply to some of the RF circuits. Okay, so some of the RF circuits, we use non-uniform sampling, and we actually get some very interesting, property. Okay, so there's a lot of interesting, exciting opportunity, that we can do. But don't worry, in this class, I will focus on uniform sampling. Okay, so this will be the only moment that I will kind of hint you how this kind of different type of ADC will work. Okay, so you have this, and you can see it's very signal dependent, right? Because your sample generated when you cross that level. All right, so what is a contention error? So first of all, is there a contention error?
Sure.
Sure, right? Because you see your staircase and you still have an error. You have a V error. How do I analyze it? How do I analyze the error? I have no idea. Okay, uniform sampling is sampling ADC. By the way, I think that's one of the reason why 99.99% of ADC in the world is uniform sampling. Easier to understand, easier to analyze. I can even show you the equation to calculate. Here, what is it? I have no idea. Okay, so that's why I said it's a research project. So over the years, my current and former students, they have done a tremendous job to try to understand what's going on here, whether there's some interesting property that we can gain. In fact, we did surprise the world. So sometimes the students go and present to the outside world, and everybody will say, "What the heck is this? What the heck is this?" So I have people design ADC for 30 years, and come to our students' presentation and say, "Yeah, what is this?" Right. So that's where you're gonna have a divide. You have some research, and hopefully some of the technique ends up to be useful. Okay. So the bottom line is that what is the spectrum looks like? By the way, this is just one type of non-uniform sampling ADC, right? Like I said, there are many other type of non-uniform sampling ADC. This is just one type. This is called the level crossing, right? So you really just do amplitude quantization. So it turns out that, right? So this is the output waveform, right? So the sample will generate depends on when your input signal will cross a certain level. If you look at the spectrum, do I see the input? Let's say this is 127 Hertz sine wave. Do I see the input?
Definitely. Yes.
Yes, you have to. That's the first thing that you have to see. Inject a sine wave, you see nothing out. What's going on? Your circuit is not working. or you forgot to power up. It's still powered down, right? So you see nothing. All right, so you see this? Do you see the quantization errors? You do. You see these tones? This is what we call the harmonic tones. Okay, so you have a sine wave, this. Harmonic means that it's integer multiple of this. Okay, so those are the quantization errors. When does that end? So this second harmonic, third harmonic, fourth harmonic, fifth harmonic. When does that end? It never ends. It just go to infinity. Okay. So just to show you, yeah, even though I did show you how this is a PDF function, how to do this, right? But it depends on how you design the ADC, the outcome can be quite different. Okay, so that's my only point. However, this is what I'm gonna turn this back to the uniform sampling ADC. Uniform sampling ADC, basically I have a sampling action here. What does the sampling action give you? If I sample the FS, what happens? So from the signal processing lectures, aliasing. It will alias at every what? Every integer multiple of fs. Can you imagine if I tell you, yeah, every fs you fold it? Every fs you fold it? Go to infinity, yeah? every FFC folded. We get back to this. Okay, so there's still a certain relationship, back and forth, between non-uniform. I mean, in this case, this level crossing or cross-level, quantization. There is still some certain relationship between this and that. Okay, so I just want to point that out. This is actually a very interesting topic, out there. In fact, the Signal Processing Society, they have been actually studying this for decades. So the first time I showed this, some of the theoretical people, Signal Processing Society, they come talk to me and say, Mike, yes, we please do more of this, right? So they study this, theoretically, they prove that this is possible. Yeah, they just for some reason so far no human being actually was able to produce enough interesting non-consuming ADC in real life to show them that how that can be beneficial, right? So that's kind of a research topic. Unfortunately, some of our past students and some of the current students are still working on this to find out some of the interesting property and that can help to minimize the cost of the ADC. Okay, so I'm running out of time. So I will, any question? I think this is a good point to stop. Yeah, I think it's a good point to stop. Okay, so I'll stop right here and no class on Monday, so we'll see you next